Thanks first to Bermudian for putting such a wonderful symposium and providing me the opportunity to speak. As the title suggests, you can see I will talk about something about score-based diffusion model, which is nowadays a very powerful tool in generative modeling. For people who might not be familiar with this tool, its connection with dynamic systems and the control might be a bit unclear. So I hope through my talk I can show you this interesting and close connections between score-based diffusion model and the dynamic systems and the control. And I believe you will see more evidence tomorrow on these connections, because I see there will be multiple talks on this topic. Okay, but yeah, so first let me start with the background why we are interested in using score-based diffusion model to solve inverse problems. So inverse problems consist of recovering some interest of a quantity of interest x from a measurement y, and here we assume we know the measurement model capital F, and with some possible noise epsilon. So yes, this is a very central topic in a lot of computational disciplines like computational biology, imaging, medical imaging, astrophysics, geophysics, etc. And typically there are two formulations for inverse problem. One is point estimation. You want to find a single best possible x through certain optimization problems. So the objective consists of two terms. First is the fidelity error, measure the distance between the real measurement and the inferred measurement from your x. And the second term is just regularization term. So when your measurement is sufficient and the noise is small, so point estimation is usually sufficient. But if you have a lot of noise or you do not have enough information for measurement, then it becomes impractical or even impossible to infer a single best possible x. So a natural goal for inverse problems becomes, okay, infer the possible x as a distribution. And in this sense, Bayesian sampling is a natural framework. So by Bayes' rule, you know the posterior distribution of x will follow such a term consists of two parts. The first is, again, the local likelihood of your observation, and the second term is prior. Okay. And usually, the less information you have regarding the measurement, then the more important the more important the prior is. And traditionally, this prior of the data is somehow kind of handcrafted with some heuristics. But nowadays, as you will see in a minute, it becomes more realistically to model certain high-dimensional data prior. Okay, so this is the background, and either for point estimation through optimization or Bayesian sampling. Okay, the gradient-based method is our major computational tools. So here on the left is just gradient descent, and on the right, if you want to sample some x from px proportional to exponential of minus fx, we can apply some stochastic variant of the gradient descent called Langevin dynamics or Langevin Monte Carlo to sample the target distributions by adding some additional Gaussian noise terms to the gradient descent. But we know for both algorithms, when f is convex, okay, we have very nice guarantee of the convergence of the algorithms. But when f is non-convex, especially equipped with many local minima, then the gradient-based methods can suffer. We need much more global information to help identify the solution. And the worst case can be exponential with respect to the dimension d, the so-called curse of dimensionality. Yeah, and recently we know, okay, machine learning or deep learning has become a very powerful tool for high-dimensional computational problems. And inverse problems is very suitable for machine learning because its formulation, as you see, naturally involves both data and physics. And across the whole community, there are a lot of works showing the strengths of using machine learning to help solving inverse problems for both scenarios of point estimation and the Bayesian sampling. So today, I will talk about a recent work collaborated with John Bruna from NYU on using score-based diffusion model as a model for data prior to provably sample posterior distribution. Okay. So in order to talk about posterior sampling, I have to first talk about the prior distributions. Okay. So the prior distribution means a distribution of data of your generic interest without any further measurement or further knowledge. Okay, and it is a very classical task in statistics and machine learning, and usually it's used to be very difficult for high dimension data. Again, due to the curse of nationality. But in recent years, the rapid advancement of natural modeling based on neural networks has made assumption of high-dimensional data prior much more realistic. So nowadays, you must have seen such kind of pictures generated by different generative AI tools like DARA3 or Stable Diffusion. So these image generators essentially function as certain samplers, okay? Because they can sample realistic images we see in our real world. And this, you can think these models learn an implicit distribution from data sets that exist with large scale. And the mathematical models behind, at least one typical mathematical models behind these things are called score-based diffusion. It consists of two dynamic processes. One is the forward process starting with your clean data distribution at time t equals 0, and you running the forward SD keeps adding more noise through the Brownian term, and up to certain large time, the xt will behave very like the Gaussian noise. And the goal of score-based diffusion is trying to reverse this process in the distribution sense, such that you can start from the Gaussian noise distribution and finally end up with x0, which provides you the clean data distribution of your interest. And in this process, in this reverse process, the key quantity is called the score diffusion. It's the gradient of the log density respect to xt at any intermediate time. Okay. So in other words, we are trying to find dynamics or vector fields defined through the score functions to guide the noise to our data. So now you can see why it is related to dynamics. We are trying to find such dynamic systems to replace the classical use of Gaussian, the Langevin dynamics. Yes, because I think I need to comment that although dynamics looks very similar to Langevin, as it also involves the gradient of the log density, but the mechanism is quite different. For Langevin dynamics, it's kind of equilibrium thermodynamics. It can take a very long time to sample non-convex or log concave distribution. Even for simple distributions like Gaussian mixtures, but the reverse SDE works like non-equilibrium dynamics. As long as you have a very accurate score, you can sample those log concave distributions with finite time. Okay, but how to find those reverse dynamics or score functions? There are multiple ways. One popular way to find the loss function is the score function is through the so-called score matching. So you can see it's very straightforward by matching the score in the least square sense. And when you have clean data x0 with some mathematical manipulation, you can transfer these loss functions into another least square type loss function depending on the clean data, so that the optimization is quite easy for this kind of object functions. And in terms of optimizing dynamics, you can imagine there are alternative approaches like a neural ODE type of approach, but the optimization respect to the neural ODE type approach, it will involve spec propagation through time, and which are more difficult to optimize. So recently we extend the score matching concept for general modeling to general stochastic optimal control problems by keeping the benefits of this kind of regression type loss landscape, which facilitates training. I don't have enough time to go into details, but I just want to point out because I think it might be interesting to this community on stochastic optimal control problems. Okay, so let me go back to the sampling task. Okay, so both theory side and practice side, people have studied these systems intensively in recent years. Nowadays, we have a quite a relatively complete understanding of this reverse dynamics process with some comprehensive error analysis going beyond the local concave sampling. So the questions we are interested in, okay, suppose we have a reliable tool or reliable reverse dynamics generate data, prior data of our interest. How can we transfer the power of prior data sampling to the posterior data samplings in a provable way? Okay, this is just the new target. We want to sample on top of the original prior data distributions. Okay, so yeah, I hope you are still following me because finally I'm defining the mathematical details of the inverse sampling problems. Okay, suppose our prior data is pi, and our forward process in the score-based diffusion is just a standard OU process, and assume we know some accurate time-dependent score respect to the reverse dynamics. Now we have a measurement model which is linear, denoted by the matrix A. The dimension of output Y can be different from X, and the X here X we assume X lives in the D dimension, and the noise is certain Gaussian noise, isotropic Gaussian noise respect to standard deviation sigma. Okay, so under such a assumption, you can immediately write down the likelihood of the posterior distribution. So it is just a quadratic tilt on top of the original prior distributions pi x. So here the linear term b doesn't matter too much on the difficulty of the task. The key quantity is the quadratic matrix Q defined by A transpose times A divided by sigma squared. Okay, so our goal is to sample. You can imagine our goal is to modify the original reverse dynamics so that we can sample this new target distribution mu instead of original pi. Okay, but before I go into the details, let's first look at this matrix Q, because we can easily identify certain easy regimes where this task is easy to sample. First, imagine if the smallest eigenvalues of Q is very small, is very large. That means the quadratic terms dominate the whole data distribution. So then you can think the data distributions, the posterior distributions mu becomes strongly low concave. Okay, this just means your measurement noise is very small. Okay, you are very confident of your measurement, and the matrix A is a full rank. Okay, so in this case, long-term dynamics is sufficient to give you a faster sampling of the posterior. In another extreme case, when the largest eigenvalue of Q is very small, okay, which means your measurement is very weak, okay, you barely do not observe much information from your measurement, okay. So you can imagine in this case, the posterior distribution will be very close to the prior distribution because you do not get much more information from the additional measurement. Okay, then you can imagine I can use the prior as a baseline and do some importance sampling to adjust the weight, okay, which is a natural baseline in this case. Okay, so these two facts are quite universal, okay, independent of the score-based diffusion. But the interesting thing is that with if you have the reverse dynamics, a reverse SDE, giving you the prior data distribution, now you can do something more in the middle. Okay, So let's first think about a special case. If the matrix Q is somehow proportional to identity matrix, okay, then this task seems very compatible with our reverse SDE, because in our forward process with OU process, we are just keeping adding a lot different levels of isotropic Gaussian noise. Okay, actually with some calculation by matching the signal to noise ratio, you can show that if you define the capital T star as follows, defined as the signal to noise ratio, and define the y quota as e to the minus t times the y, okay, then the condition distributions of x0 conditional on xt star equals the y quota is exactly your target posterior. Okay, so in other words, if you run the reverse SDE from a specific time t capital T star, and with your initial condition for the reverse SDE as point distribution y quota, then you can recover the exact posterior of your interest by running the reverse SDE from capital T star to 0. Okay, so this is a nice observation, and our main result is trying to generalize this result for the general Q. Okay, so the key reason we can make this generalization is because under the linear measurement model, the quadratic tilt part has a very compatible structure with our reverse SDE or the original prior data. So we can consider a time varying quadratic tilt in such a form and indexed by t. So here pi tx is just the intermediate data distributions defined by the forward process, and this is just a quadratic terms. And we define q0 equals q and b0 equals b. So when t equals 0, mu 0 is just the target distributions of our interest. But the nice thing is that, okay, if we for the t where this ODE dynamics is well defined, then we can initialize xt according to distribution mu t and run the reverse SDE from t to 0. Then we can know that xs will follow the distribution of mu s for any intermediate time, and specifically then x0 will give us the decided posterior. Okay, so why will this give us a good result to make the sampling easier? The implication may be not very clear at this moment, but let's look at the solution of these ODEs. Okay, it has a quadratic terms on the right hand side. You can expect it will blow up with finite time. Okay, I'm plotting the analytic solutions of the eigenvalues of Q with different initial conditions. So you can see they will blow up at different time. Okay, and the key observation is that this blow up actually brings us something nice. Why? If you consider the special case I introduced in the previous case, if Q is proportional to identity, then all the eigenvalues will increase with the same rate and will blow up at the same time, and then the whole the whole distribution mu t at that blowout time will become a delta distribution. Okay, a delta distribution is very easy to sample, and then you transform the original sampling problems of mu 0 to a new sampling problems of mu t, which is easier to sample. Okay, so that's the nice thing of this tilt transport technique. And for people of the dynamic system community, you will see just like the linear quadratic control problems or common field. Okay, under this linear quadratic structure, again we can have something beautiful in mathematics to relieve the computation task. If I put it more specifically, you can think the posterior sampling problems for mu t will be provably easier than the original posterior sampling problems of mu 0. Why? Because this new sampling task mu t, you can interpret as a new posterior target. Its prior is pi t, okay? Remember, the original pi 0 can be very complicated, multimodal, non-log concave, but under the OU process, pi t will get closer to the standard Gaussian. So pi t will become less multimodal. That means pi t is the easier prior. And for the likelihood term qt and bt, remember the eigenvalues of qt keeps increasing. So that means your quadratic chance becomes stronger than the original time. So the likelihood or the measurement information also becomes stronger. So both easier prior and easier likelihood contributes easier posterior sampling. And then we can start from this new posterior sampling and run reverse SD to finally achieve our goal. This is just a scheme plot of this whole idea. So I'm using Gaussian mixture example. So on the top is the prior data distributions. So the top left is our prior data distributions, consists of 25 modes. So you can see that the density is highly non-log concave multimodal, and we can start with the standard Gaussian distributions and running the reverse SDE to sample this posterior to sample this Gaussian mixture distribution. And then the bottom left is the target posterior distributions under certain measurement. It's still multimodal with updated weights. And if we apply our tilt transport technique, the new posterior or boost posterior we need to sample at the T star is much nicer, as you can see. Although it's not log concave, but it's very close to log concave, and it's much easier to sample. And after we sample it, we run the same reverse SD, we get our target posterior of interest. And we can make quite precise characterization when the new posterior will become log concave, such that the long-term dynamics can efficiently sample it. Suppose our original prior distribution is a convolution of a finite support distributions mu with some isotropic Gaussian with variance delta. Then we can show that the new boosted distributions mu t star is strongly log concave if the following condition is satisfied. So there are 4 parameters involved. One group is delta, which means the smoothness of your prior, and R, which is the support of your prior. So these 2 parameters denoted by blue are the properties of your prior distributions. And another 2 parameters is signal to noise ratio and kappa A, the condition number of your measurement A. So these are 2 parameters of your measurement model. So these conditions gives you very rich insights how the difficulty of your posterior sample task depends on these 2 group of parameters. Okay, so I'm plotting these 2 phase diagrams to illustrate this point. Okay, so suppose you have a fixed combination of delta and R, so you have a fixed prior. Then you can plot in the space of condition number kappa A and the signal to noise ratio where this condition where the left-hand side equals the right-hand side under this condition. So you can see these level curves are all U-shaped. Okay, that means if you look at the figure horizontally, okay, for the region inside this U-shape, this is a difficult to sample region, and for small signal to noise ratio or large signal to noise ratio, the problems becomes easier to sample. Okay, so this is a nice thing compared to classical long-term sampling or impulse sampling I just mentioned. With this reverse SD dynamics, we can cover both areas on the left and the right simultaneously with the same framework. Okay, and another thing you can imagine, if we look at the effect of signal to noise ratio or condition number, as we increase the signal-to-noise ratio or decrease the condition number, the condition becomes easier to satisfy. Okay, that means as long as we have a better measurement model, the task is also easy. And we verify our theorems with numerical experiments on high-dimensional Gaussian mixture samplings for d equals 20, from d equals 220 to 40 and 80. So you can see, so here again the x-axis is signal-to-noise ratio, and the y-axis is the statistical distance of the samples we obtained respect to the two distributions. So the lower the better. So the long-term dynamics, okay, can do very good job when the signal-to-noise ratio is strong, which is low concave, but the error will increase quickly when signal-to-noise ratio is large. And in contrast, if we use our tilt transport technique, the statistical distance is very small for both small signal-to-noise regime and large signal-to-noise regime. Even for the difficult regime in the middle, its performance is still much better than the larger ones. Okay, and the first result is just a special case of our analysis technique, and we can make it more general, but due to time constraint, I will skip it. And we also have another example for the sampling task, which comes from the statistical physics called the scalar field 5-form model. Okay, we can interpret as a posterior sampling if we view the first part as a prior and the second part as a likelihood in a quadratic terms. Okay, and people know, okay, as beta, the inverse temperature increases, there will be strong correlation of the field, and the target distribution becomes much more difficult to sample. And we compare again the effect of Langevin and boosted Langevin under our technique with different beta. You can see as for these three temperatures, we can always reduce the autocorrelation time of the dynamics. That means we get faster sampling compared to the Langevin. And not surprisingly, as beta increased, the task itself becomes more and more interesting, difficult, and our acceleration effect will get reduced. And we also have some preliminary results on the inverse problems on images. The first column comes from original data, and we have degradation model from observed data. And we have some pre-trained large-scale diffusion model as our data prior. And if we use some existing method to do the inverse problems, which seems somehow some is okay, but with some artifacts. And if we use our boosted version, the effect, the performance is improved. Okay, so this is my last slide. To conclude, the score-based diffusion model allows us to model complex data distributions from data set through certain dynamics. And it also allows us to provably solve inverse problems with moderate conditional linear model and complex priors, okay, through modified dynamics. This is the main part of our work. And a natural question remains open, is that how can we use some similar idea or with other techniques to modify dynamics to solve zero noise, yield-conditioned, nonlinear inverse problems, which are more challenging. Okay, so I will stop here. If you are interested, please take a further look of the paper or talk to me. Thanks.